results in proving inequalities. And recently, we have developed a software which is called AITIP, which is a web-based software, which can help us to prove information inequalities or to give us hints about how to construct a counterexample if AITIP cannot prove the inequality. So proving information inequalities are very useful when we want to analyze a communication system. Now, for example, if we look at the data processing inequality, here we consider a system which has a data source X, okay? And then we measure it, and then we get some raw data Y. And then we process the raw data Y and get the outcome Z, okay? So here we say that they form a Markov chain, X, Y, Z. Or in the language of information theory, we use mutual information to describe the system. We say that the mutual information between X and Z given Y is equal to 0. Under this constraint, we can prove that the IXY is larger than or equal to IXZ. And the insight from this formula is that the correlation between IXY, if we do some processing here, we cannot increase the correlation comparing with the output Z here. So this one, the correlation is smaller comparing if you use Y correlated with X. Or in another example, the perfect secrecy theorem. So in this case, we want to, we have a secret message U, and then we want to make sure that the encoder can encode the message U and then generate a ciphertext X. And we want to make sure that they are completely independent. So that X, we can feel safe to send it over the internet. At the receiver side, after getting X, and using the shared secret randomness R, which is shared with the sender, then the receiver can decode the original message U without any error. So this is the model. And in information theory, we describe it as the independency. We use IUX equal to 0, and it can recover the original message. We say that the conditional entropy of U given RX is equal to 0. Using these two constraints, we can prove that HR is always greater than or equal to HU. The insight we get from this formula is that if we want to achieve perfect secrecy here, that is UX are independent, then we need to initially share the secret randomness, which must be larger than or equal to the message size in order to achieve this. So from these two examples, we can see an applications of proving information inequality and how it can help us to analyze a communication system. Now, so far we have seen some simple inequality using 2 free random variables. However, in many cases, we may prove information inequality involve more random variables. And then this job is non-trivial to prove them. Now, say for example here, if I tell you one of these 2 inequalities are correct, another is wrong, so can you tell me immediately which one is correct and which one is wrong? I think after some calculations, you can find out which one is correct, but you will still find that, okay, it takes some time, it takes some effort. And especially when we want to derive a result for a system, okay? We want to model it, and then we want to prove an inequality. Actually, we may not be sure which inequality we want to prove at the beginning. Just like this example here, at the beginning, maybe, okay, we believe the first 4 terms are something like this, but for the last part, we may try, okay, maybe this conditional entropy or maybe some other terms, we don't know. So we may need to try a lot of inequalities when we model a system, or at least more than 1 or 2. And also maybe under different constraints, different assumptions. Then it will become a very time-consuming job. And that's why it will be very nice if we can have a computer to help us to do this. So in 1997, Yang proposed a framework for linear information inequalities. And then later on, Yang and Yan developed MATLAB program called ITIP, which can help us to verify an information inequality. And after that, there are many different other software packages have been developed, and they can help us to verify an information inequality on a computer. This is very nice. And now let me show you the example using XITIP to verify the inequality we have seen before. Now, suppose we plug in this inequality into XITIP. After we click this one check, then we see this box here. So it says that this inequality is not solvable by XITIP. And it says that the inequality may be true, may be not true, or it is a non-Shannon type inequality, and it can be true. So I think at least you can agree with me that the message here seems to be not very conclusive. We are not very sure whether the inequality is true or not. And later on, I will go back here to, I will give you the clear definition of what we mean here by the non-Shannon type inequality and the meaning of this box. But at least we can see that it is not very conclusive for this inequality. And for another one, this is very good. We have a good news here. At least we see the word true here, okay? Then does it mean that, okay, now we have this inequality, we can immediately put it into our paper and then submit it and use it as one of the steps in our proof? If we do this, we may, very likely, we may receive a review comment saying that we need to further elaborate this step because it is not very clear how we can verify or how we can see this inequality is true. Because in fact, what we want is a proof like this, okay? We want to have at least one more steps to tell us that this part here can be rewritten into another form. Here, all the terms here are non-negative, so that we know if the summation of them, it must be non-negative as well. Then we can feel safe to use this inequality, okay? It is always larger than or equal to 0. And furthermore, we also need to, we also want to have this proof because from this proof, we can see the terms here, and it gives us an insight when the equality holds in this inequality. So just like this example here, if we want the equality holds, then it can only happen if all the terms here are equal to 0. Because if any one of them is positive, all the other terms are non-negative, this term cannot be cancelled out. So that's why a proof can also provide us the necessary and sufficient conditions for the equality to hold. And this is very important because usually we use information inequality to find the limits of the system. And if we find the conditions for the equality, then it gives us the insight about how to decide the optimal system. And another important application is that using computer can help us to solve some problem which is much bigger. For example, here, Charlton had in 2013, he solved an open problem in distributed storage system, which involved 16 random variables. So you can see that even 4 random variables, it may take us some time, and 16 random variables, if it is very complicated and difficult to solve. And he tailor-made a linear program for the required inequality and then find the converse result and the proof. So in this case, in this example, we can see that computer can help us to tackle some problem with large size. Okay, now let us start with talk about how we can find the proof by using a computer. And first of all, I need to introduce some notations here. Now, suppose we consider n random variables, there are x1, x2 up to xn, and then we denote the joint entropy of all the non-empty subsets of them by the vector h. So what I mean here is that now suppose we have only 3 random variables, then the vector h will contain the entropy of x1, entropy of x2, x3, so on and so forth. And then the last one is the joint entropy of all the random variables. Then we can input our information inequality into a computer using this format. So say, for example, here, if we want to put this information inequality into a computer program, we can simply denote it by a vector b here. So the conversion is like this. Because this information inequality, we don't have entropy of x1, we don't have entropy x2. So we put 0 in front, corresponding to these entropies here. Except the last two terms here, we have minus entropy of x1, x3. So we put the coefficient -1 here, the second last part. And the last element here, we put +1, okay, for the joint entropy of all of them. So we can use B to denote this information inequality, okay, in the system. And for this entropy vector, we know that it cannot take arbitrary values because they are a set of joint entropy. So they must satisfy some inequality which we know. So the well-known one are due to the non-negativity of Shannon's information measures. And I want to save space. Now here I just use two random variables as an example. And for two random variables, we know that, okay, all the conditional entropy are non-negative, mutual information is non-negative, and also all the entropy and joint entropy are non-negative. So that's why we have 6 inequalities altogether here. But here you can see that actually the last 3 can be proved or rewritten in terms of the first 3. For example, here, this inequality, we can basically use the first one and the third one, and then combine them together, we can get this inequality back. So in other words, this is not a minimal set. And to save the computational resources, we want to use the minimal set and put into the computer. So that's why in this example, we will consider only the first 3, okay? And we call it the elemental inequality because it forms the minimal subset of all the inequality due to the Shannon's information measures. And then in this case, we will construct a matrix D to store these elemental inequalities. And the way is that just like how we store B here, because for example, the first one, we don't have entropy of x1. So we will store a vector 0 and then -1 and then +1 as the first row in D. And then the second row is -1 and then 0 and then +1 into the second row. And then the last one, of course, is 1, 1, -1, okay, into the matrix D. Here we have seen an example for 2 random variables. Of course, for n random variables, we can have a general form and we will use these formulas to generate the matrix D. Basically, they are the conditional, suppose we have n random variables, we just pick any one of them, and the first inequality is the conditional entropy of xi given all the other random variables, which is larger than 0. And then we transform it into the joint entropy and then put into the matrix D. And then another set is generated by the conditional mutual information. We picked any pair and then condition on the subset of the rest of random variables. And then we generate another set and then put into the lower part of the matrix D. And we have seen 2 examples at the beginning that they are the data processing inequality and the perfect sequencing theorem. In those examples, we have seen that in those problems, we usually have equality constraints which are given according to the system definition. So it is very common that we have some equality constraint we need to input to the system as well. So we will use a similar idea to convert all these equality constraints into joint entropy and then put into a matrix E. So you can see that, for example, here, the first example, we have 1 equality constraint, then the matrix E has only 1 row. And for the second one, we have 2 equality constraints, then the matrix E will have 2 rows altogether. When there is, suppose in some problems, we don't have any equality constraint, then we can simply use E as an empty matrix, or we can simply drop it in the calculation. Okay, now let me first tell you what is happening in ITIP and XITIP when we plug in an information inequality and ask it to prove. So what it does is that because now suppose you are given an information inequality and together with the equality constraint, suppose there are n random variables, then the system will construct the matrix D for n random variables according to the 2 formulas for the elemental inequalities, and then construct the matrix E. And in this picture, it is, I use this gray area, this cone, to denote this inequality here. That is, they want to solve a linear program which minimize this term subject to this constraint. And the gray area here are the all feasible points which satisfy the constraints here. And let us first look at the picture on the left-hand side, and this is how we define the cone. And then for this information inequality, BH, we want to minimize it. So if we see it in this picture, what it means is that we want to draw a line here, and then we want to move it to the left bottom side until we can still touch the feasible set in this cone. And we move to a point that, okay, this is the limit, and then we find the minimal value of this inequality. Here, I use a convex cone because all these inequalities here are linear, and also they pass through the origin. That is, when you substitute h equal to 0, then it is equal to 0. So that's why I draw a cone here. And then from this picture, you can see that if the minimization is equal to 0, that is, the touching point is at the origin, it means that all the feasible points inside this region is above this inequality. That's why we can prove that, okay, this inequality is always true. Because if we generate a point using the Joyce entropy, it must set using the Joyce distribution, the entropy must satisfy this elemental inequality. So that if we randomly generate a Joyce distribution, the point must be somewhere here, and it is always above this line. And in this case, we also give it a name. We call it, it is a Shannon type inequality. Okay. So for another case here, if the given inequality actually it cuts through this gray area, and in this case, if we run this minimization program, so what it will do is it finds that, okay, we can always pull this line, that is the inequality, to the right-hand side if we want to minimize it. Okay, if we minimize it, okay, we can pull it to the right-hand side. And because it is an infinitely convex cone, we can pull it to the left, to the right-hand side to infinite. So that's the optimal value is minus infinity. So when XITIP or ITIP find that the minimization value is minus infinity, so it means that the line cut through this gray area, it will claim that this problem is not solvable. We are not sure whether this is true or not. Okay, so this is the basic idea of ITIP, and so this is the theory. Okay, but if we implement it in MATLAB, actually there's something funny will happen. Is that if we actually put a true inequality and then run the linear program in MATLAB, very likely we may not get exactly 0 here. Okay, from this program. What we get is maybe something like 10 to the power minus 12, or sometimes a very small minus 10 to the power minus 12, this kind of value. This is due to the floating point error, the precision, which can be used in the MATLAB or in our computer. So that's why the optimization algorithm will stop at that point. They say that, okay, this reached the limit of the program. But of course, I think we will tend to believe that, okay, this inequality is true because the value already reached the limit of the MATLAB program. because another case that we expect that it will go to a very large negative number. But at the end, you may, if you see the program give you such result, you're still a little bit unsafe to use the inequality. And this is another motivation why we want to see a proof, so that we can verify the inequality is correct or not. And so we will propose our solution here, and we will solve another linear program, which is basically the Lagrange dual of the problem, which is considered in ITIP. And it is given in this format. So basically, we still use the same matrix D and E here, and then we find the feasible solution Y and mu such that it satisfies these two constraints. And random variable and the variable Y must be non-negative. And you can see that the objective function here is basically useless because it is always equal to 0. So the basic idea, the most important thing is we want to find a feasible solution which satisfies the constraint here. And it is still a linear program. So in this slide, you can see that what we do here is basically reconstructing the given vector B as the linear combinations of the rows in the matrix D and E. And in this problem, we are exploring the algebraic aspect of this matrix. And it is different from the geometric aspect we have seen in the previous picture. Here, as long as we find a feasible solution, then we can solve the problem. So why this is important, I mean, how can we get the analytical proof from this linear program is due to the following theorem. Now, suppose an inequality is Non-Shannon type, that is, it is true. If and only if there exists a feasible solution, Y star and mu star, which are solution to the following, that is the linear program we have seen on the last page. And then from this Y star and mu star, we can construct a proof using this format. That is the given inequality can be rewritten in this form. And then we can show that it is always non-negative. Now, let me explain these slides here through an example. It will be easier. Now, suppose we want to prove the perfect secrecy theorem. That is, the entropy of R is larger than the entropy of U, subject to these two constraints. Then the program will see that, okay, there are 3 random variables. Then it constructs the matrix D, and then construct the matrix E according to this given constraint, and then solve the linear program on the previous page here. Okay, and then I get a feasible solution. And in the feasible solution, the Y star has a lot of 0, except 2 elements are equal to 1. And for these 2 elements equal to 0, it doesn't really matter because 0 times this term, it will just give us 0. But for the term which are equal to 1, then we pick up those rows in the matrix D here, and then write down here in the red color, okay? So basically they are coming from 2 rows in matrix D. And then similarly, we do that for the elements which are positive in the vector mu star here from the feasible solution. And then we pick up the corresponding row in the matrix E. And remember, in the matrix E, the rows are corresponding to the equality constraint. So that's why from the feasible solution, Y star and mu star, we can construct a proof like this, okay? So now, let us first verify this is a proof. So here, the program tells us that the given information inequality, okay, this is something we want to prove. We want to prove if we put this HU term to the left-hand side, it means that we want to prove HR minus HU larger than or equal to 0. The program tells us that we can rewrite this one as the following format. And we can check that easily by canceling out the joint entropy here. So for example, the first one is HUX. I found that if I share the screen here, I may not be able to draw something on the PowerPoint. Okay, so I just use a pointer here to show you. So the first term here, HUX, is cancelled out with the last term here, okay? Because they are all minus sign, but we have a minus here. So they will be cancelled out. For the RUX term here, it is also cancelled out due to the minus sign here. And then HX, they are cancelled out due to the minus sign. And then RX is also cancelled out here due to the minus sign here. So what we left is only the R, entropy of R minus entropy of U. And this is equal to the left-hand side of this equality. And then notice that the first two terms here are coming from the elemental inequality. Actually, they can be rewritten as Shannon's information measures. So this is basically conditional entropy. This is mutual information. And we know that they are non-negative. And for these two terms, we have negative sign here, but they are actually equal to 0 because they are the given equality constraint. So that's why we can put down larger than or equal to 0 here. So this is how we get a proof from the linear program, okay? So we can see that the linear program, what it does is basically we expressing the given information inequality in terms of the elemental inequality and also the given constraints, okay? However, it is natural to ask, is there only one way to do this re-expression, or is there more than one way to do it? Now, let's look at this example. Suppose we want to prove this information inequality. And if we run the program, or if we check that, actually it can be rewritten in 3 different ways in terms of the elemental inequalities. So we know that, okay, all these are valid proof, okay? We can use any one of them to check this one is non-negative. However, it is also correct that this one can be rewritten as the linear combination of all the 3 inequalities here, and then we get a format like this. And of course, this is a very ugly proof because it is big, it is unnecessarily big, okay? What we want is a simple proof like maybe just 1 line here. Then this is what we prefer, and then we can get more insight from the proof. So this motivates us to consider a problem, what we call the shortest proof. That is a proof which involves the least number of elemental inequalities and the equality constraints. Now, let's look at the linear program we have used it before. And as we have discussed it, the objective functions here are basically useless. So we can modify this part to change this to become the L0 norm of the y and mu vector. Okay, so what we want to do is to minimize the cardinality of these 2 vectors so that we can minimize the number of inequality and the constraint involved in the proof. However, using the L0 norm here to make this linear program, to make this problem, this optimization problem complicated to solve. So we will relax this problem by, instead of considering L0 norm, we consider the L1 norm here. Since y is always non-negative, if we consider the L1 norm, we can simply take the y out and then we can just look at the vector mu here. So this is a convex optimization problem. It can be solved by interior pointer method numerically. But we can also further transform it to the following equivalence problem by introducing variable z, so that we can again use linear program to solve this problem. So basically what we replace here is that instead of using an absolute sign here, we don't want to have absolute in our objective function. We replace it by a linear function in terms of z, and then we require that mu must be upper bound and lower bounded by z and minus z here. Then these 2 problems are equivalent. And furthermore, here we will expand the matrix D here. So far we have discussed that we use the matrix D to contain only the elemental inequality. Actually, it is also okay to expand it to contain all the basic inequalities which are due to the non-negativity of the Shannon's information measures. So at the end, we get a combination of the rows in D. It is still a valid proof because they are all non-negative. So if we do this, if we plug in this inequality into the system, then we will get a proof like the final line, okay, the last line here. If we don't expand the D, okay, if we only use the elemental inequality, then the system will give us the second line because it only knows the elemental inequality. It actually doesn't know that entropy of X is larger than 0. So you can see that here, the linear program actually learns the mutual information measures through the matrix D. So if you put more terms or more rows into the matrix D, then the linear program can learn more Shannon's information measures, and it can give us a shorter proof. However, we need to pay the price that if we use a large matrix D, then the computational time will be longer because the size of the matrix is bigger. Then it takes more computational resources. And also, I want to tell you one thing that, so now we said that, okay, we use this L1 norm thing to approximate the original problem. We consider the L0 norm here. But actually, they are two different problems. So what I mean is that now let's consider this example. Suppose we want to prove this information inequality, okay? It can be, this one can be rewritten into these two forms, okay? So they are both a valid proof. We can see that they are both non-negative. For the L0 norm, it prefers to give us, it will give us this solution because the cardinality here is 3, okay? But if we consider the L1 norm, basically it is adding the absolute values of all the coefficients in terms in front of the Shannon's information measures. So in this case, they are all equal to 4. And so it is possible to get any one of these two lines if we use the first linear program. So we leave it as an open problem about how to efficiently make a program which can check the L0 norm or give a better approximation result, or how we can format the matrix D so that we can teach the program more Shannon's information measures in an efficient way. But now let me show you another interesting modification of the linear program we see here. Now you see that here we want to minimize the summation of the coefficient for using the elemental inequality and also the coefficients in front of the constraint here. Now suppose we drop the first term. We only look at the constraint. That is, we remove only this part, the y is disappear. We only consider z here. So this is another linear program which will give us the minimal set of equality constraint. That is, we only want to minimize the set of constraint we used in the proof. Now let me demonstrate you the application through the example which is copied from Young's book. So this is called the implication problem. In this example, we want to prove the mutual information, the conditional mutual information between x and y given t is equal to 0 under these assumptions here. So if we want to prove this one is equal to 0, first of all, we notice that this guy is actually always non-negative. So what we need to do is to prove that it is smaller than or equal to 0. Then we can get that this term must be equal to 0. So in other words, we want to prove that the negative of it is larger than or equal to 0. So this is what we put into the program. And then we put these 5 constraints into the program, and then we run this linear program, and then we get this proof. Now, in this proof, we can see that the first 2 terms are basically coming from the elemental inequality. They have the plus sign here. And the last 3 terms, they are negative. and they come from the equality constraints here. And in this proof, we can see that basically the last two constraints we see here are useless because they are never used in the proof. We only need the first three constraints. So we can see that we can reduce this problem by making smaller amount of assumptions. And another interesting observation is that if this guy, now we can prove that it is equal to 0. If it is equal to 0, then these two terms must be equal to 0 as well, because yeah, they're all the terms here are non-negative. So in other words, we can see that if we make the assumptions in the first line here, we can immediately imply that we can prove that these two quantities are equal to 0 as well, because they are these two terms here. So it is interesting to know the minimal set of equality constraint for information inequality, because when we consider a system, at the beginning, as we discussed before, we may not be very sure which inequality we want to prove, and then we make some assumptions. Sometimes we may make some unnecessary assumptions in the problem, and then in this program, it can help us to reduce the amount of assumptions to the minimal set, and then we can have a result which requires a smaller amount of assumptions, so that it can be applied to a more general cases and can be used in more scenario. So this is why we are interested to know the minimal set. Okay, so this is the story for an inequality which can be proved. Then how about an inequality which cannot be proved? So at the beginning, we have seen an example that we put the equation 2 into the XITIP, we get not solvable. So now let me explain to you what is happening here in ITIP or XITIP if we put this inequality into the program. So as we said before, the first thing is that we can interpret the program as, okay, it will construct a convex cone based on the elemental inequality and the given constraints. And actually this cone here, if we somehow we can plot all the feasible edge, that is, now suppose we are given 3 random variables, and suppose we have enough computational resources, we just exhaustive all the joint distribution of 3 random variables and then put a red dot in this picture, okay? Although it is a high dimensional for 3 random variables, it should have 7 dimensions, but somehow let me show you in a 2-dimensional picture to get the idea, okay? Now suppose we can exhaust all the feasible points, okay, by using all the joint distribution and plot it here. So the elemental inequality tells us that this point must be inside the gray area because they must satisfy these inequalities. And then in the proof, okay, if the inequality is true, we say that the gray area is always above this line, and the point it touches is when it is equal to 0. It is at the origin, okay? So if this is the case, it also guarantees that this red region here is above this line, okay? So that's why we feel safe, okay? This inequality is true. Another case is that if the inequality cuts through the gray area here, then in this example, it also cuts through the red region. So we are not sure whether this inequality is true or not, okay? Because it cuts through the region. So we believe that, okay, it should be false if we can find a point here, just like the pointer here in a region, in this red region, we have a point under the line, okay? It is inside the red region, then we can prove that this inequality is wrong. However, there is no guarantee that the red region is exactly equal to the gray region here. Just like this example, we only know that the red region is inside the gray area, but we don't know whether there can be a small gap. And this problem was solved by Zhang and Yang. In 1997, they proposed a constrained non-Shannon type inequality. And then in 1998, they proposed a unconstrained non-Shannon type inequality. So what it means is that if they give an example, it shows that when there are 4 random variables, it is possible that we can find an inequality which cuts through the gray area, which is constructed by the elemental inequality. However, this inequality is true. It means that no matter how you generate, how you try different choice distribution, and then you generate the vector H, you plug into this information inequality, you can always see that it is positive. The red region is always above this blue line. So that's why if the program finds that the inequality cuts through the gray area, it is not it is not conclusive. We don't know whether this blue line is, your given inequality is just like this blue line in the gap, or the given inequality is like this black line actually cutting through the red region as well. So that's why if we want to show that an inequality is wrong, we need to find a counterexample, which is a point inside this red region, but under the black line. So in other words, we want to find a choice distribution such that we can disprove the inequality. And in the following, I'm going to show you how we can get some hints about how to construct the counterexample by using linear program. And the idea is the following. And here I need to use one more notation called E. Basically, this is a column vector which has 0 except the last element is equal to 1. So that if E multiplied with H, we will get the joint entropy of all random variables. And now we want to solve this linear program here. Comparing with the previous one, the difference is that we have an extra term here, plus E gamma, and the objective function is minus gamma. We want to maximize it. And then after we find the feasible solution, by looking at the Y star and the mu star, if we can find a choice distribution which satisfies this constraint, then we can use it as a counterexample to disprove the given inequality. And again, let me use an example to illustrate what we mean here. Now, suppose we are given this information inequality. We want to prove that the IXY is smaller than or equal to 0.9 times the entropy of Y, okay? We plug it into the AITIP. Then we get the following message. It says that, okay, maybe this is a non-Shannon type inequality, or this inequality is basically not true. And if it is not true, we can try to construct a counterexample using the following conditions. So what happened in the program is that if we plug in this inequality in the program, it tried to solve the linear program here, okay? And it doesn't have any equality constraint in this case, so we can forget about mu. And it gets a vector Y. Again, the vector Y, that is the feasible solution, we call it Y star, okay? The Y star has a lot of 0, except 2 places. They are equal to 1. And then we pick out those 2 corresponding rows in the matrix D, and then write it down here, okay? And together with the requirements that the joint entropy of all random variables has to be bigger than 0, okay? So from these conditions, this is the hint given by the AITIP or from the previous linear program. So from the hint here, we can see that, okay, what it says is that we want to construct an example, the conditional entropy of X given Y, or the conditional entropy of Y given X are both equal to 0. If this is the case, okay, if we find a choice distribution like this, we can give us this, then this can be used as a counterexample. And in this case, you can see that basically we can just let X equal to Y. Then in this case, X equal to Y, then IXY is basically equal to the entropy of Y. So it must be larger than 0.9 times the entropy of Y, as long as the entropy of this random variable is larger than 0. So this is what the AITIP can give us. And now let's put the equation 2 into AITIP and then see what we can get. And in this case, we will see a more complicated hint. Okay, there are a bunch of Shannon's information measures here. Of course, I mean, it is difficult. It is more difficult for us to see the counterexample from this hint, and we leave it as an open problem about how to write a computer program which can automatically convert all these hints into a valid counterexample. However, I can share with you some experience about how to use the hints here. Just like the hint here, we first look at the conditional entropy. So here you see that we have some conditional entropy. Given the other 3 random variables, we can construct the 4th one. Okay, this is the first 3 which tell us. So it will motivate us to consider an example which has 3 underlying random variables. Let us call them x, y, z. And then to construct these 4 random variables as the function of these 3 random variables. Okay, and then usually we use the mutual information and conditional mutual information to give us hints about how we put the exclusive OR, and then to construct this example. And then for this one, you can try, it will be not too difficult, let me say in this way, if you use this approach. Then the next important question is, okay, now AITIP will always give us some hints if we cannot prove a given inequality. But does it mean that we can always construct a counterexample from the given equality constraints? And unfortunately, the answer is no, due to the non-Shannon type inequalities. Such as if we put the inequality found by Zhang and Yang, okay, this is a non-Shannon type inequality. If we put into the AITIP, it still gives you a set of equality constraints. It asks you to construct a George distribution such that all these quantities here are equal to 0. If you can do this, okay, then you can disprove this given inequality. But of course, we know that we cannot do this because it is always true. And the only case you can satisfy all this equal to 0 is that all the random variables are basically constant. So that's all the terms here are equal to 0. But if this is the case, all the terms here are also equal to 0, then it is an equality sign here. So that's why in the counterexample, we require that the entropy of the George distribution of all random variables has to be larger than 0. So we won't get some trivial counterexample which cannot disprove the given inequality. But does it mean that we cannot use AITIP to prove non-Shannon types inequality? Or let me say in another way, what it means by non-Shannon type inequality, if we say that we can consider this problem in an algebraic approach. So what we have seen so far is that now if we are given an information inequality which has n random variables, AITIP cannot prove it if it is a non-Shannon type inequality, okay? Because non-Shannon type inequalities are those which are true but cannot be reconstructed as a linear combination of the elemental inequalities involving only n random variables, okay? Because we construct the matrix D using only n random variables. Then it is very natural to ask, how about if you give me an inequality using n random variables, how about we construct D, which has more than n random variables? Just like this one, okay, it has 4 random variables. How about we construct matrix D using 5 random variables? If this is the case, can we prove this inequality? And the answer is yes, but we need to pay some tricks here. Now, suppose now we put this information inequality into AITIP, and furthermore, we put these equality constraints into the program. AITIP tells us that, okay, we can prove this, okay, you can check that this one, the inequality can be rewritten in this form, which is equivalent to the combination of these quantities here. And they are coming from the green one are coming from the elemental inequality. They are Shannon's information measures. They are always non-negative. The blue one are due to the given constraints here, so that they are all equal to 0. We don't need to worry about the minus sign. So that this guy is always non-negative. Okay, we can prove the inequality. And we claim that here, the constraint here it doesn't limit our possible choice of the P, A, B, C, D here. So in the given inequality, we have only 4 random variables, A, B, C, D. But here in the constraint, we introduce an auxiliary random variable E, so that the AITIP will construct the matrix D according to 5 random variables, okay? Because we have 5 random variables here. But if we look at the constraints here, we can see that basically for any given George distribution P, A, B, C, D here, we can find a George, we can define the random variable E according to this distribution. That is P, A, B, C, D multiplied with, we generate E using the conditional distribution of A given C, D. Or let me explain it using this figure here. Now, suppose we have a George distribution A, B, C, D, okay? We first generate random variables C and D. And then from the output, we use the conditional distribution to generate random variable A, B. Then if we just look at A, B, C, D, the George distribution must be the given A, B, C, D here, the P, A, B, C, D here. Now we construct an auxiliary random variable E, which is generated according to the value of C and D, but using the conditional probability distribution of A, just like this picture here, okay? And you can see that actually the George distribution of ECD is equivalent to George distribution of ACD, and also given CD, AB and E are independent. So that's why these settings, we can satisfy all the constraints here for these auxiliary random variables. So in other words, this constraint only limits our choice of E, but actually the proof here is valid for any George distribution for P, A, B, C, D, okay? Of course, another way, if you think it is non-rigorous to using this picture, you can also check it by summing any variables here to get the marginal distribution to show that, for example, the marginal distribution of AD here is equivalent to marginal distribution of the DE here. Then we can also prove all the equality constraints here are valid for this choice of E. And okay, finally, let me tell you one more result before we end this talk. In some problem, okay, as we said, we want to prove an information inequality, okay, under some constraint, okay, we want to model a system. This is the constraint we have. Unfortunately, we put into AITIP, it says that it is not true, and we believe that it is unlikely to be a non-Shannon type inequality, or we may even find a counterexample. So we want to add more assumptions to the system. We really want to prove this inequality to be true, okay? We want to add some extra assumptions or extra equality constraint to the problem. And let me call it F. So that this equality is true if both F and this set of E, we know that we must make this assumption, okay? Altogether, this becomes true. And we can also all use linear program to help us to find this matrix H, matrix F. And the way to do it is by solving this linear program. And the idea is very similar to what we discussed before. That is, after solving this linear program, we just look at the entries in the feasible solution, that is Y. Look at the entries which is positive, okay? We pick up the corresponding rows in the matrix D. As long as you set the equality constraint in those elemental inequality hold, okay? That is DH equal to 0 together with your given equality constraint, then we can verify that this given inequality is true. Okay, so to conclude my talk, so in this presentation, we have seen how we can use linear program to get an analytical proof for an information inequality. And we also talked about how we can get the shortest proof and find the minimal set of having a given set of equality constraints, how we can find the minimal of them in order to get the proof. And of course, there are some open problems regarding how we can find the shortest proof. And for another case, sometimes AITIP cannot prove a given information inequality. In this case, we can use AITIP or the linear program to give us some sufficient conditions, which we call hint to construct counterexample to disprove the information inequality. And also in some cases, we can also use linear program to help us to find extra equality constraint such that a given inequality can become true. And this is a joint work with Alex and Chiwei and also Raymond. And you can find our online tool in the website, okay, here. And okay, so this is the website. You can put in the inequality here. And for example, this is the non-Shannon types inequality we have seen before. For example, you can submit and then you can check your results depending on how complicated your problem is. And then after you wait a while, you click the link and then you can see the results here. And the results here is explain everything in terms of joint entropy. Of course, you can rewrite it in terms of Shannon's information measures to make your results more compact. Okay, and if you are interested, you can find more information about these results in our papers. And I also want to say that in this homepage, you can find the link to the source code of the linear program we discussed here for making the AITIP. We believe that there are still many open problems. We can expand this program and to tackle different problems. So yeah, so thank you. So this is all.